Today we have the pleasure of having Ahmed Almheiri, who will tell us about holography on the quantum disk.
Right. Thanks a lot, Juan. You gotta pick menu first. Yeah. Okay, thank you, Juan, and thanks very much for the organizers for organizing this conference and inviting me to speak. It's always a pleasure to be back at the Institute, and I'm really happy that we're keeping the IIS December conference tradition going. It looks like there's indeed life after it from Qubit. So I'm going to talk about some work in progress with Fedor Popov, postdoc at NYU. Here he is with Chris Nolan, although I'm not going to tell you who is who. So I think he's somewhere here in the audience. Okay. Yeah, I was about to say. No, I think neither of them are here. Okay. So I should say that Fedor was absolutely key for this project for two reasons. One is his great mathematical agility, and also equally important that he speaks Russian. This is a very math-heavy subject, and a big chunk of the literature is in Russian. And also, Fedor is on the market this year, so keep a lookout. So the topic of quantum spaces is a bit foreign to our community, although some people here have worked on it. So my talk is going to be about just one specific example, and sort of as a soft introduction to the topic. All right, so let me begin with some broad motivation. So we often like to ask, under what conditions does smooth semi-classical spacetime emerge? We often answer using slogans: entanglement, strong coupling, chaos, or large N. More basic question is, from what does it emerge? Or as Joe once said, what are the atoms of space? All of these ideas or questions are central for understanding holography, the black hole interior, factorization problem, the stock market, etc. This talk is going to be about some aspects or the physics of an example of a pre-emergent spacetime. So one model or hint of an example of that comes from the double-scaled SYK model, which is the limit of of regular SYK, where you take to infinity both n, the total number of fermions, and p, the degree of the interaction Hamiltonian, or the number of fermions participating in each term. That's why it's p for the number of fermions participating. Anyways, so you take those two to infinity while keeping lambda p squared over n fixed. In this limit, you get the so-called chord description of double-scale SYK, governed by a bulk Hamiltonian composed of a chord creation and annihilation operators that satisfy this algebra. So this is not the standard commutator, but a Q commutator having this factor of Q squared here. This chord picture is well, you should think of it as a pre-emergent spacetime. And what the chords actually are, they just represent Wick contractions between insertions of the Hamiltonian. For instance, the chord method of computing the partition function, the thermal partition function, is to Taylor expand it and then evaluate the moments by Wick contraction averaging over the Gaussian random couplings. And this picture here, I stole from a paper of Henry and Douglas. Smooth spacetime emerges in the large beta small lambda limit, where the number of chords proliferates and fills out the spacetime, giving you hyperbolic space. This chord picture suggests that the bulk is discrete. And so what are the signs of discreteness? Well, the Hilbert space of this chord theory is spanned by these Fock states labeled by n, where n is supposed to represent the length or the length of a wormhole with some discrete length n. This interpretation follows from computing or studying the behavior of boundary anchored correlation functions, for example, the two-point function, which is evaluated in a definite n state, is evaluated to be e to the minus delta, the dimension of the operator, times n times lambda. So n times lambda is like the length of the distance, or rather the distance between, the bulk distance between these 2 points, measured in units of lambda. Now, lambda in this model is like a minimal length, And it actually turns out to be the semi-classical parameter. So lambda is kind of like the ratio between the Planck length and the ADS length. So this is the length in units of the Planck length, morally speaking. There are signs of non-commutativity in double-scale SYK coming from, which follows from the observation that there's a symmetry algebra that moves particles around while keeping the bulk background fixed. And as shown by Henry and Douglas, this is a subalgebra of UQ SU1, 1, which is the algebra that generates the quantum group SUQ1, 1. I will describe what these things are in a few slides. These are so-called quantum deformations of the standard Lie algebra group SU1, 1. Okay. There are also signs of a, well, the hallmark of non-commutativity is to have what is called a non-trivial coproduct. What do I mean by coproduct? Well, well, just from the name, a coproduct is simply just a rule for acting on products. For standard Lie algebra, the action satisfies a Leibniz rule. So if you act on a product, just a Leibniz, for example, the derivative operator. But for a quantum algebra, there can be a sort of twisting, that when you act on the second element, the first one picks up some transformation. So more precisely, coproduct is when you study the action of your algebra on a tensor product module, for example, where this is some element. So this module is just a vector space that the algebra acts on. And if you have a trivial coproduct, for example, for SU1, 1, then some generator E looks like this. But for this quantum group, it's going to have this extra term here that implements the twisting. It turns out that there's a, so you might think that that's just a, it arises because of the bulk is discrete, like in the chord picture, but actually some aspect of it survives in the continuum limit of double scale SYK. If you take lambda goes to 0, but keep temperature finite, this is known as large PSYK, then there's a secret SL2 symmetry in this system, which you see only after doing some funny coordinate transformation. Take, for instance, the 2-point function in the theory. So in large PSYK, this is what the 2-point function looks like. It doesn't have the standard SL2 form. But if you do this coordinate transformation where you transform theta1 and theta2 in slightly different ways, relating them to some other variable phi, then the 2-point function indeed attains the SL2 form. This parameter V is just related to the temperature in this way. That's not important. It's instructive to see how the symmetry acts on these operators on the physical coordinate theta, or on the fake coordinates phi. So let's compare those two. So here's the 2-point function. So here's an example of the action of one of the SL2 generators on the product of operators in terms of the fake coordinates. So it just acts in the usual way, and this is one of the generators of SL2. But if you just take that expression and you just change coordinates back to the physical coordinates, then you find that the action of the symmetry is a bit weird. Well, it has a twisting. So the generator E, in terms of the physical coordinates, looks like this. We can also define this generator K that shifts the angle, and you find that the action of the symmetry, well, when it acts on the first one, it's just E on the first one, but then when you commute it to act on the second, you have a twisting by K. Yes.
When you say E, exactly what you mean? This big symmetry group there. Some particular generator of that group, or you mean any generator, or what are you saying?
One generator. Oh,
yeah.
No, well, here is just one of the generators. There are a total of 3 generators.
Yeah.
Yeah, this is one of them.
Okay.
Just an example.
Okay.
Please slow me down.
Looks like an expectation value. So that's...
Drawing the horizon, Neil. Okay. 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 So killed my flow, man. Okay. So this. All All right, so all of these observations motivate us to understand these non-commutative aspects and quantum groups a bit better. And so I'm going to consider a very simple example, which is to define this quantum disk. Okay, so here is the outline. So we finished the motivation. I will define this SUQ 1, and its associated generators or generator algebra UQ SU 1, and this will be used to define the so-called quantum disk, basically the space-time that's invariant under these the action of this group in algebra. Then we'll study aspects of matter fields propagating on this quantum disk. Then some comments about the symmetry of the putative boundary dual, and end with some outlook and open problems. I should say that much of this material was already done by Waxman a long time ago in Russian, and part of what we do here is translate it to English and also reframe it in terms of holography. Okay, so first quantum groups. So the quantum group SL, first we start with SL2Q. In its defining representation, it's all 2 by 2 matrices where these matrix elements are not just regular, they're not C numbers, but rather they're non-commutative variables that satisfy these relations. Okay? These relations are often called ideals. This one in particular is what's called a quantum determinant. As you take Q goes to 1, it's just a regular determinant. Okay? These relations or ideals are not picked randomly. They're picked to satisfy some properties. One is that they provide an ordering. Okay? Second is that if you have any polynomial in A, B, C, D, the ideals cannot be used to change the degree of the polynomial. For these two conditions are guaranteed by solving an R matrix equation, where these G's, these are a group element, so G11 is like A, where R here satisfies a Yang-Baxter equation. Okay, so in what sense is this quantum group a group? Well, it has an identity element, something that's obtained by the so-called co-unit, and also has an inverse obtained by the antipode. So you need those two things, but you also need group multiplication. So, so multiplication here, so there is group multiplication, but not in the naive sense of just taking 2 copies of this matrix and multiplying them together, because there's a constraint that you need the product of 2 group elements is another group element where the product has to satisfy the same ideals. One way to do that is to implement a sort of tensor multiplication. So you take the multiplication happens in 2 copies of the group. So in this way. So this looks like just standard matrix multiplication, but there are tensor products. Okay. This group also has a coproduct, which is what you use to construct tensor factor representations. It acts in this way. It takes A, B, C, D to these combinations, which is essentially just matrix multiplication, but in the tensor product fashion that we just described. Again, the constraint is that you want this tensor factor representation, or rather you want the components of the matrices in this tensor factor representation labeled by delta A all the way to D to satisfy the same ideals as A all the way to D. Okay? And that's what the coproduct is built to do. Okay, so but we don't want SL2, we don't want SL2Q. So in the classical case, SL2C is what maps the complex plane back into itself, but we care about the symmetry that preserves the unit disk, and that's given by SU1, so we care about the quantum deformation of SU1, that's obtained, again, just like in the classical case, that's obtained by applying a reality condition. So you have this operation star, which is some involution on the algebra, and it has you have to impose this condition, which well, and when this is true, you're talking about SUQ 1,1. So that was the group. Next, we talk about the algebra. So, or rather, the generators. So if you start with SL2Q, then the generators are denoted as, or the generator algebra is UQ SL2. In one basis, you can write down K, E, and F as the generators that are defined through through a pairing, where K pairs with A and D, E pairs with C, and F pairs with B. All the other pairings are equal to 0. So this is equal to 1. Morally speaking, what this means is this just tells you in which direction do these generators move you on the group manifold. So E is like a derivative with respect to C. F is like a derivative with respect to B. K is Q to the derivative with respect to A or D. Okay, so K is really the exponential of a generator when cast in the classical case. Okay. If you take the pairing of these generators with a group element, then you have these three matrices. Well, this is what the matrix representation looks like. Okay. For consistency with this pairing under tensor products, that implies that K, E, and F have to satisfy the following coproduct rules. Okay? So just like similar to what we saw at the beginning in the motivation, so the coproduct of E has this twisting, and so does a coproduct of F. Okay. The pairing. So because the A, B, C, D had some relations between themselves, the ideals, using the pairing, or rather the pairing implies a set of relations or ideals on K, E, and F, which look like the following. People usually just start with this algebra, defined as the algebra of UQ SU1, 1, but I showed you the path to deriving them. This algebra has a Casimir given by this. There's also a reality condition on these generators in order to be the generators of UQ SU1, 1, and here it is. Okay, so that was everything about the symmetries. Before I define the quantum disk, are there any questions? Okay, so let's talk about the quantum disk. Okay, recall that ADS3 is isomorphic to SL2R, and that ADS2 is a quotient of that. You can do the similar thing here. You can define the quantum disk in the following way. You consider a copy of SUQ 1, where these matrix elements satisfy these ideals and this determinant relation. To get the quantum disk, you have to mod out. What you can do is mod out by the right action of K. Just as a side note, you get different, you get ADS2 in different coordinates by considering different quotients. Okay, but this is the one that I'm going to consider. The way that the symmetry group acts on the quantum disk descends from how it acts on these matrices. So from just left group action, just standard matrix multiplication. And you can show that T prime and T satisfy the same relations. Through the pairing between K, E, and F and A, B, C, D, you can derive how the generators K, E, and F act on these coordinates T, I, J. For instance, just a thing to highlight is that K is a rescaling. Okay, but now we need to implement the quotient. The way to do that is to define coordinates on your ADS, to define coordinates, which are functions of Tij that are invariant under the right action of K. Since K was just a rescaling, you can define, if we define Z as T21 inverse times T11, you find that, well, this combination is invariant under the action of K. And its conjugate is the following, is this. These two are they are related through this star involution or whatever, because of the reality conditions that we impose on the matrix elements. Because Tij satisfied these relations or ideals, that imposes the following commutation relation between Z and Z star. Okay? So this shows you that these coordinates are non-commutative. Okay? That's where it comes from. If you define Y to be 1 minus Z star, then you find that that Z star, and Y satisfy this algebra. In one representation, you can write down a Fock space that defines for you, quote unquote, points on the quantum disk. Y is diagonal in this representation, and it's equal to it's integer valued at q to the 2n, and Z and Z star simply raise and lower. Now recall that Y is like a radial coordinate, okay, because 1 minus Z star. And so the heuristic picture you should have in mind is that the quantum disk is a series of concentric circles, and it asymptotes to the, well, you get an infinite number of circles. Closer and closer you get, well, denser amount of circles, closer you get to the unit circle. Okay. The action of the symmetry group on the Z's is what you might expect. So if the action of the group, you just get, it looks like standard Mobius transformations, but you have to be careful that all these coefficients are not, they're non-commutative. So are the Z's. And if you go from Z to W via this transformation, again, just by consistency, well, you find that WW star satisfy the same algebra as ZZ star. The action of the generators is the following, which if you squint and you ignore the factors of Q, this is just the action of standard SL2. Okay. However, the difference is that when you act, well, the difference is that there's a non-trivial coproduct. This is the action on a single, on Z and Z star just raised to the power of 1. Next, we're going to talk about how to act on general functions of Z and Z star. So how does the symmetry algebra, for instance, act on arbitrary functions? So consider the following monomial, Z to the n, Z star to the m. The way we should think about this is that you start with a tensor factor of having n z's and m z stars, and there's a multiplication map that multiplies them all together. Okay? The action of a generator on this monomial is determined by the coproduct, where you should think of this as acting with the coproduct on the tensor factor way of writing it, implementing, well, this coproduct implements the action in this way, and then you use the multiplication map to multiply the results together. Well, the upshot is that you didn't really have to go through all this procedure. You just do it in sort of the intuitive way, just by distributing the action of E on these two, well, on the two Z's. So you get something like this. On a general holomorphic function, here's what the action looks like. For K is simply a rescaling of Z. But what's notable here is the action of E. E implements a finite difference derivative on the function of Z. This really comes from this factor here of 1 plus q squared, because if this was Z to the n, you'll get 1 plus q squared plus q to the 4 dot 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 up to q to the 2n, I guess. Okay, it's convenient to define a derivative operator that has the coproduct built in. That's a derivative operator that satisfies this algebra. So d by dz, for instance, does not commute with z. if you take it through, then you pick up a factor of q to the minus 2. So it has a twisting, as we described before. What's convenient about these differential operators is that you can express the Casimir in terms of them. And well, this is a standard Casimir in ADS2. So having done derivatives, now we talk about integrals. So just like in the usual classical case, if you take an arbitrary function on the unit disk, you can do a mode decomposition. And the integral that you define simply picks out the integral on the quantum disk that respects the symmetries of the quantum disk will pick out the zero mode. This is just a fancy statement of saying integral d theta e to the in theta is equal to 0 unless n is equal to 0. Okay. But to define the integral more precisely, we need to define a measure. Well, the measure has to be invariant under the action of SL2, and here's what it is. It's just the same measure as that you have in standard ADS2. But we just said that non-trivial integrals are only over the radial coordinate. So the measure is really just you just have a measure in the y direction with this conformal factor y to the minus 2. But recall that the spectrum of y is discrete, and hence this measure is a finite measure, which depends on where you are along the disk. What this means is that the integral will reduce to a sum. So here's an integral of some arbitrary function on the unit disk that becomes a sum over the zero mode with some weighting factor. Okay? So integrals become sums, the same way that derivatives became finite differences. Okay, so that was the quantum disk. Next is going to be, well, I'll talk about some properties of fields on the quantum disk. What that means is that I'm going to take this wave equation and just solve it. Okay, so let's focus on the S wave equation. Here it is. You have some differential operator in terms of just y, where this d is this finite difference derivative. So the Laplacian is this combination. The eigenfunctions of this Laplacian are just given by Q hypergeometrics, some special function. But what's interesting here are what the eigenvalues look like. So this is an eigenvalue parameterized by delta. And to solve the wave equation, you need to set it to equal to m squared. For the solutions to be real and to satisfy the right boundary conditions, you focus on the principal series, where delta is parameterized as 1/2 plus is. So if you plug that into the equation for the eigenvalue, you get this guy. You set it equal to m squared. Now there are two interesting properties here. One is that the range of these eigenvalues is bounded. So the Laplacian is bounded from below by 1 over 1 plus q all squared, but notably it's also upper bounded by 1 over 1 minus q squared. Okay, and so you kind of have a UV cutoff. But through the wave equation, this imposes an upper bound on the mass, which is strange. Recall that from the intuition of double scale SYK, 1 minus q for q close to 1 is like the Planck length. So this says that there's an upper bound on the mass you can have in your theory that's bounded by the Planck energy. Next, we talk about the propagator. The way I'm going to think about it is that it's a function on two copies of the quantum disk. One copy, well, we have one copy represented by these z's and the other copy with these x's. And just by symmetry, this propagator must be a function of the so-called invariant length. Here's what it is. Again, looks like the standard ADS2. And so it's some, well, here's an arbitrary function of that. But there's a subtlety here that it's, well, there's a subtlety in what you mean by taking powers of an invariant or a quantity that's invariant under a quantum group. So here's a theorem you can prove that if you have two if you have two functions that are each UQ-SL2 invariant, then the following combination is UQ-SL2 invariant. It's where you multiply them using so-called opposite product, where you essentially, the multiplication is done by sandwiching. Okay? So here, AB is inside and CD are on the outside. The reason why it's called opposite product is because, what? Okay, I can turn it off, right? Okay, okay. Okay, I'm not going to say why it's opposite. Okay, so if you apply this rule to this, you get this expression. What changes at this factor becomes a Q-Pochhammer symbol, defined in this way. So this is not equal to d to the minus 1 to the power of n. Let's look at some examples. So if you take mass is equal to 0, you find that the propagator is equal to 1 over the Q-deformed integer times d to the minus m. This is what you might define as the Q-deformed logarithm. Notably that if you take d goes to 1, this thing is finite. It's not infinite. So this Q parameter acts as a UV regulator. This had to be true because the Laplacian was bounded. Then you can talk about boundary anchored propagators, which you obtain, well, just in the standard way. Well, you want solutions that fall off in this way as you go to the boundary. Well, this is what the bulk to boundary propagator looks like. It's well, okay, let me just say it. Because you want it to fall off in this way, and propagators have to be constructed from the invariant distance, you just take the invariant distance to the power of delta, and you strip off one conformal factor, and you get this. To get a two-point function, you strip off the other conformal factor. If you take this expression and take Q goes to 1, you get the standard sign. But just for intuition, the way that you get something that looks like this is by taking the sign and writing it in this way. This is what you get by raising this expression to the deltath power, applying this opposite multiplication. There's some fakeness in this answer, in this result. If you take the boundary two-point function from the previous slide and just look at it in the small dimension limit, then the expression is not symmetric under the swapping of theta 1 and theta 2. But if you transform to some quote-unquote fake coordinates, where you transform theta 1 and theta 2 differently, then you can write it in a way that's symmetric under the interchange of the variables, in a similar way that to what happened in the fake disk story. This suggests that for the fake disk, Q is just a phase that depends on the temperature. All right, let me just make some comments about the conformal symmetry of the putative boundary. Well, the boundary coordinates are commutative, and the new ingredient is that the generators have a non-trivial coproduct. You can derive how operators transform on the boundary by studying, by using the bulk. If you take a bulk field and you act on it with some symmetry generator, and then you expand it near the boundary, then the coefficient of y to the delta is how the boundary operator transforms. And here's what it is. If you take Q close to 1, then this looks like this. You can kind of see that this is going to look like the standard SL2 transformations. The upshot is that given that the boundary operators transform in this way, this tells you that the coproduct survives the boundary limit. You can from this Q symmetry, just like the standard conformal symmetry, it fixes a two-point function, three-point function, and conformal blocks. Here's an example constraint that fixes a two-point function. The three-point function that you find on this constraint also agrees with the bulk-Witten diagram, which is computed in this way. So you take three bulk to boundary propagators, and then you have to integrate around the circles, and then sum over the radial coordinate, and you get an expression that looks like this. All right, let me end with some outlook and open problems. So sometime in the past, people were very interested with the system, well, this conformally quantum mechanical system, because it described the motion of a charged particle near an extreme horizon Northern black hole. that its Lagrangian is given by this. Something you can do, a game you can play is try to find Q-deformed versions of various models. Here, you can get a Q-deformed version of this by just simply taking this continuous time derivative and replacing it with this finite difference derivative. Wait, what? There it is. Okay. Okay, and you get so this Lagrangian is rather the action with this Lagrangian is invariant under SL2Q. One sort of question here is so one observation is that this Lagrangian defines an invariant action independent of whether you use a continuous time integral or a discrete time sum. I don't know what that means. But so this theory is a bit non-local, so maybe it's best to be defined with Euclidean time. Another question you can ask is whether there's dynamical gravity. Is there an example of a Q-deformed JT gravity? So recently this was discussed by many groups, including Blomart, Mertens, and Yao. The question is whether you can define you can define Q-deformed JT gravity as just having, it's the theory that in the bulk localizes to the quantum disk, but you have a boundary description in terms of a quote-unquote Q-deformed boundary particle that's governed by a Q Schwarzian. Here is one way you can define the Q Schwarzian, again, by doing this simple thing of replacing all continuous derivatives with finite difference derivatives. And you can show that this is indeed invariant. Final comment is that you can ask, what is the thermal state in this system? If you take the reparameterization T to be just the exponent of minus U over beta, you find that the Schwarzian is not constant in U. But if you take the reparameterization to be this Q exponential, then you get that the Schwarzian is equal to 1 over beta squared, the standard result from JT gravity. But to completely understand this, one needs to understand for an arbitrary reparameterization in this Q context, we need to understand Q-deformed Virasoro, a topic that's already been studied a lot, and thankfully I have Fedor. Okay, and just to end, I just wanted to say the Q deformation quantum groups and coproducts are old ideas, but hopefully they'll teach us something new about our current problems. Any Q questions?
Yeah, so yeah, it was hard for me to tease out the physics here. There was a lot of math. Are you saying that? Are you saying something about what is the bulk dual of double-scaled SYK in terms of like, is it some field theory on some non-commutative base or something like that? I couldn't quite tell what the punchline was, or if you've answered that question or not.
So I have not answered that question. What I discussed mainly was just about just bulk physics. You can wonder if there's a limit of double-scaled SYK that is described by this quantum disk and fields propagating on it. It's not obvious to me that there is such a limit, but if I was to suggest where to look, would be where you take lambda, keep lambda finite, but you take beta to 0. So the low temperature limit of double-scaled SYK while keeping lambda fixed.
Is that something that can be seen by comparing to the functions that Vladimir and?
Yeah, I think that would be the thing to do.
Because you also had similar looking.
Yeah.
Yeah. But they're not obviously the same.
They're not obviously the same.
Yeah, I was curious. You mostly looked at the sort of the algebraic aspect. Is there a differential geometry aspect to the structure? If you want to talk about bulk gravity, is there something like connections on manifolds that are purely
there is literature discussing that. There's a book, I think, by Cohns, but we have not penetrated that literature yet.
So I think you might have started to say this at the very end when you talked about Q Virasoro, but it feels like the radial direction is somehow very special compared to the angular direction and this Q deformed stuff. Is there any sense of like a Q diffeomorphism invariance, which sort of restores like arbitrary coordinate systems, or is the radial direction always going to be special?
No, this is just in quote unquote in one gauge. Remember you can apply a finite transformation to go from coordinate z to coordinate w. Well, remember I had this w and z that were related by some SL2 transformation. That would give you circles centered about some other point, for instance. So no, it's not. This is not special. It's just a choice of gauge.
I guess I thought that was about the isometries, not the more general diffeomorphisms. I guess I was asking about the more general diffeomorphisms.
Yeah, more generally, you need a more developed theory, which I don't understand yet.
Yeah, so sorry if this is incorrect, but my understanding is that Yang-Mills in a non-commutative space can be rewritten in terms of Yang-Mills plus higher order interactions coming from strings or something like this. Could it be the case that here you can also re-express this theory on a non-commutative space as scalar field plus higher order corrections?
Well, you can just naively just take, let's say we just discussed the boundary theory. So you can just take this and then just, oops, and then just, so these are finite difference derivatives, just Taylor expand. So this is going to give you a theory with infinite number of derivatives. Whether it has an interpretation in terms of strings or not, I guess that maybe depends on the specifics of the non-commutativity.
Can you use this quantum disk thing to compare some non-resolving double square SYK, for example, the two-sided wave function or the Fourier function? How is that related with this chord basis?
Yeah. To answer your latter question first, I don't know. But for the first question, this is what I said a few moments ago, that you need to identify what is the limit of double scale SYK where you expect to get a quantum disk discussion in the bulk. What I was suggesting that it might be the finite lambda small beta limit.
Valid for all range of parameters.
No, so the quantum disk, I did not derive it from double scale SYK. I motivated it from double scale SYK. Now the question is whether I can match them.
Is the quantum disk the deformation quantization of the usual disk? And maybe related to that, can we make a quantum disk background in string theory with either a B field or with like a cross of omega background or something like that?
I think the answer to your second question is just yes. I think the fuzzy sphere is an example of a quantum deformation of well, in that case of the sphere. But I don't know enough to give you explicit string constructions. But for your first question, yes, the quantum disk is a deformation of the standard hyperbolic disk, but I've defined it through deforming the symmetry group first, and then finding the space that's invariant under that symmetry group. So sort of a roundabout way.
Functions on that quantum, there's this non-commutative algebra of functions on this quantum disk. And I was wondering if that's a star deformation a la Kontsevich of the usual functions on the usual disk, because then you might be able to make a connection with like a B field or something.
Okay, let's talk afterwards.
Okay, let's thank Ahmed again.